Hello and welcome. In this video, we're going to be taking a look at a unique kind of series known as a power series. Now, just like with other series, we have a sum of infinitely many terms, and we're kind of interested to know if it's convergent or divergent. But what makes a power series a little different than some of the series we've already looked at is that it has a variable in each of those terms. So in each term, we'll have a variable such as, say, x, and it'll be to a different power in each term. So let's take a look at a definition. Power series is where we have a series of the form of a sum from n equals 0 to infinity of Cn, which is some kind of coefficient, times x to the power n, where x is a variable. So that gives us C0 plus C1 times x plus C2 times x squared, and so on. You can see each term has a degree that is higher than the previous term. Now, it doesn't necessarily have to start n equals 0, and we don't necessarily have to have x to the power n. We could actually shift this power series. And if we were to write x minus a to the power n, then we would say that that is a power series centered at a. And a standard power series, x to the n, that would be centered at 0. Now, what does it mean for a power series to be convergent? To get a better sense of what convergence means in a power series, it might help to take a look at an example. Let's start off with an easy one where all of the coefficients are equal to 1. So that's this series from n equals 0 to infinity of x to the power n. And that gives us 1 plus x squared plus x cubed, and so on. And so we know that as we start adding more terms, the power continues to get larger and larger. So this is a polynomial where all the coefficients are 1, but we can't really talk about the degree of the polynomial. The degree is infinite. But, well, we do know that for any value of x, let's just say like x equals 2. Well, 2 to the n, that's a geometric series. And so actually, no matter what x is, we can treat this as a geometric series where r is equal to x. And because it's a geometric series, we know when it converges. It would converge whenever that ratio has an absolute value less than 1. That means that in this case, it's convergent when the absolute value of x is less than 1, and is divergent when the absolute value of x is greater than or equal to 1. Now, what this gives us is actually an interval for x. The absolute value of x has to be less than 1 means that x is a number between -1 and +1. And, well, this is a polynomial, so we're saying it's convergent over an interval for x. It's hard to kind of grasp that without maybe looking at a little visualization. So I've got Maple open here so we can take a look. So here I've got that series, n equals 0 to infinity, except I've just left that as k for now, of x to the power n. So keep in mind that this is supposed to be an infinite series, but let's just take a look at the partial sums. Maybe we'll start from n equals 0 to 5. So that's this polynomial 1 plus x squared plus x cubed plus x to the 4 plus x to the 5. That's a polynomial of degree 5, and what we're going to do is graph that. But I'm going to start graphing multiple different partial sums. Let's start off with maybe the first 50 partial sums. Now I'm going to go from n equals 0 up to k, and I'm going to start with k equal to 1. So that's actually going to be 1 plus x. And we're going to go all the way up to a polynomial of degree 50. So these are partial sums, and watch this little animation here. This graph here is when k is equal to 1. So I'll just show you that. That's the graph of 1 plus x right there. I'm going to click on this and just go to the next frame. Okay, we've got a parabola now, and that's actually the graph of 1 plus x squared. Doesn't look a lot like the last graph, but we're getting someplace. Let's just increase the frame to the next one. There's frame number 3. You can see it's a cubic. Well, that's this partial sum. 1 plus x squared plus x cubed. And you can imagine that the next frame in this little video here is going to be a quartic, degree 4. Now look at what's happening here. We're getting a small change in the behavior of this function, but not much of a change between -1 and +1, that interval of convergence. So now let me just go back to the beginning of the video and let me play through this thing, and you can see all the way from a linear polynomial all the way up to a polynomial of degree 50. You can watch k going up one at a time, And of course, polynomials are going to be flipping back and forth here, but overall, we're not seeing really any change in the shape of the graph here, even though the degree of the polynomial is increasing all the way up to 50. So we could say that it is convergent, in fact, from -1 to +1, because the actual shape of each of these partial sums has the same general shape over that interval. So it's a little different. That's our idea of convergence with a power series. Over some interval, or some particular values of x, as we start to include more and more terms in our partial sum, the shape of the graph remains the same. Now let's take a look at some other examples here. Let's take a look at this power series that also seems to be alternating. We have -1 to the n, x to the n all over 2n plus 1 factorial. For what values of x is this series convergent? Well, the moment that we see factorials in there, the most useful test here might be the ratio test. Now remember, with the ratio test, we are going to be taking the ratio of an plus 1 over an, taking its absolute value, and looking at the limit as n goes to infinity. That can be really useful in cases where each term is some sort of fractional expression, to change this into an plus 1 times the reciprocal 1 over a to the n. Let's try this test out. An plus 1 is obtained by changing all of the n's in our expression to n plus 1. And you have to be a little careful in the denominator there. 2n plus 1 becomes 2 times n plus 1 plus 1, all factorial. And then we multiply that by the reciprocal of an. Now we're going to try to simplify this and maybe also get rid of that absolute value if possible. At this point in time, though, we can see that there are some similar looking factors in the numerator and denominator, so let's group this up into separate fractions. Now this 2 times n plus 1 can be simplified to 2n plus 3. So now we've got 3 separate fractions, one involving -1 to various different exponents, one fraction involving x to various exponents, and one involving factorials. And by a property of absolute values, we can actually take the absolute value of each of these individual fractions and then multiply them together. Now this first particular fraction is just powers of -1 being divided. That can only ever be positive or -1. But when we take the absolute value of that, we end up having this ratio equal to 1. Now, that starts to simplify things already. We can just take a look at this second expression. X to the power n plus 1 divided by x to the n is simply just x. Now in that case, x is any real number. We're trying to find out what values of x we will end up with a convergence series, so we don't know if x is positive or negative, and we won't be able to simplify that absolute value. Finally, in this third expression, we have 2n plus 1 factorial over 2n plus 3 factorial. Now the bigger of those two numbers is the denominator. So why don't we split the denominator factorial up into the first few terms? 2n plus 3 factorial is equal to 2n plus 3 times the next number down, 2n plus 2, times the next number down, 2n plus 1, and it's a product of all the numbers less than 2n plus 1, so maybe we should just write that as 2n plus 1 factorial. In the numerator, we also have 2n plus 1 factorial. And that means that these 2n plus 1 factorials can cancel each other out, and we're left with 1 in the numerator. Now, to simplify this limit problem, remember that we're only taking the limit as n goes to infinity, and we're trying to find out what values of x will end up with a convergence series. It has nothing to do with taking the limit as n goes to infinity, so we can take this absolute value of x and move it out front of this limit. And now we're simply taking the limit of 1 over 2n plus 3 times 2n plus 2. And in fact, since I know that n is always going to be greater than or equal to 0, this is always positive. And we could even change these absolute value signs to just simple parentheses, since it's already positive. But that's a kind of a moot point, because what's happening as n goes to infinity is that this fraction becomes smaller and smaller and eventually approaches 0. So we have the absolute value of x times 0, which means that this is equal to 0, regardless of what x is. By the ratio test, we have convergence whenever this limit is less than 1, which is the case that we have here. And that means that this series is convergent no matter what x is. So we say that this series is convergent for all x. or over an interval from negative infinity to positive infinity, all real numbers. Now, once again, let's go and take a look at Maple and get a better understanding of what convergence over all real numbers looks like. So here I've got that series ready to go, and let's take a look at the sum of the first 5 terms from n equals 0 up to 4. So this is an alternating series, 1 minus 1 over 6x, 6 is 3 factorial, plus 1 over 120x squared, 120 is 5 factorial, minus 1 over 5040x cubed, and 5040 would be 7 factorial. And you can just see that these factorials grow very large very quickly. And as we get to higher and higher powers of x, these coefficients are actually getting very, very small. Now, let's try graphing this over a much larger interval for x, from x equals negative 50 to positive 50. Since we know this is converging over all real numbers, we might need to zoom out a little bit. And let's take a look at 50 of these partial sums and see what happens to the graphs of those partial sums. It takes a moment to compile, so bear with it here a moment. There we are. So this is just the graph of 1 minus 1/6 x. That's just the first 2 terms. And if we go one more here, this is the graph of 1 minus 1/6 x plus 1 over 120 x squared. That's that parabola. The next one's going to be the cubic, and so on. Let's take a look at this animation. Okay, well, it kind of looks anticlimactic. After about, well, let's see, the 4th, 5th, and 6th frames, and then after that, it really doesn't really change much. So why don't we zoom out even more? Let's maybe zoom out more on the right-hand side and make this go up to, I don't know, 300. Okay, now I've really zoomed out. Let's take a look at these partial sums again. And again, even though I've zoomed out substantially farther, it looks like as I plot these partial sums, they are all converging to the same shape. And now let's really zoom out. Okay, play this one more time. Sure enough, it's converging way the far out there as well. Now it's also converging for negative numbers, but the graph goes right off my axes, off the top of the page, so it's going to be really hard to see that convergence there. You'll have to just trust that now we end up, even with all of these partial sums, having the same graph for all real numbers. So let's take a look at a quick little theorem here about the behavior of power series. This theorem says that for any given power series, let's say it's centered at a, or if we don't have x minus a to the n, then we would just say it's centered at a equal to 0. Well, then there are 3 possibilities for the values of x where this power series is convergent. It's going to be possibility number 1, it's only convergent when x is equal to a. And that could be when x is equal to 0 in the case where a is 0. So it's actually only convergent at one particular number. As we start to include more terms in our partial sum, the graphs aren't looking anything like each other at all. It's quite possible, as we've seen now, that the series converges for all real numbers, like that last example. The more terms that we include in our partial sum, you can see that the graph of the power series is starting to look more and more the same. There's also the option that we saw in this first example, where there's going to be some sort of positive number where the series converges within that little radius. R here is known as the radius of convergence. And that's like that first example that we saw, where it only converged when the absolute value of x was less than 1. From negative 1 to positive 1, centered at 0, we saw that the graph was converging. That's called the radius of convergence. Now, to extend that idea of the radius, if it is only convergent at a single number, we will say that the radius equals 0. And when the series converges for all real numbers, we say that the radius is infinite. That gives us this idea of extending the radius to all 3 scenarios. The radius could be 0 if it's only convergent at a point. The radius could be infinite if it's convergent for all real numbers, or the radius is always just some other positive number. Let's take a look at a couple more examples of finding this radius of convergence and see if we can understand what it looks like graphically. Let's take a look at the power series from n equals 0 to infinity of n squared over 2 to the power n times x minus 5 to the n. Now, the first thing to note here is that this is a power series centered at x equals a, where a is 5. We just say it's a power series centered at x equals 5. Now, once again, to find out where the series is convergent, it's probably best to use this ratio test again. Applying the ratio test, let's take a look at this classic form of n plus 1 times the reciprocal 1 over a to the n. This gives us n plus 1 squared times x minus 5 to the power n plus 1 all over 2 to the n plus 1 multiplied by the reciprocal. That's 2 to the n over n squared x minus 5 to the n. And let's group some common terms together. You can see that we have our n plus 1 squared in the numerator and n squared in the denominator. We can group those two things together and maybe just write that as n plus 1 over n all squared. Now we also have a 2 to the n in the numerator and a 2 to the n plus 1 in the denominator. So maybe we can split that 2n plus 1 up in the denominator and write that as 2 times 2 to the n. That's going to help us to simplify those couple factors. And then finally, we have some similar components with x minus 5 to the n plus 1 and x minus 5 to the n. And we can split up that x minus 5 to the n plus 1. And that gives us x minus 5 times x minus 5 to the n. Now it's time to start simplifying factors, and maybe we can simplify some of the absolute value symbols. Well, first of all, n plus 1 over n is already being squared, and so its absolute value is just equal to itself. We have 2 to the n over 2 times 2 to the n. The 2 to the n's cancel out, and we're left with 1/2, which is already positive. And finally, we have x minus 5 to the n canceling x minus 5 to the n, and we have x minus 5. Now, it depends on what x is. We don't know if x minus 5 is positive or negative, so we'll have to keep the absolute value around that factor. And much like last time, any of these factors not involving n can be moved out front of the limit. In this case, we have the absolute value of x minus 5 all over 2 not being dependent on n. And by a limit law, we can actually take the limit as n goes to infinity of our n plus 1 over n, and then we'll take that result and square it. And that's a fairly simple limit. N plus 1 over n as n goes to infinity approaches 1. And that can be shown even just using L'Hopital's rule if you like. This means that that ratio, and taking the limit as n goes to infinity, is the absolute value of x minus 5 all over 2. Well, this time around, we didn't just get a number, so we can't just say this is convergent for all real numbers or divergent. It is dependent on what x actually is. So remember, with the ratio test, we know that this is convergent whenever that ratio is less than 1. Let's start off with that and solve for x. Starting with the inequality, that the absolute value of x minus 5 all over 2 must be less than 1, we can solve that for x. We have to remember how to solve an inequality first of all. We can multiply both sides by 2, and that gives us the absolute value of x minus 5 less than 2. Now geometrically, that means that our radius is 2. But if we wish to turn this into an interval, we can think that our interval of convergence is 2 units on either side of our center point x equal to 5. We can even turn this absolute value inequality into a sandwich inequality. X minus 5 needs to be between negative 2 and positive 2, and we can solve the inequality for x by adding 5. So adding 5 to negative 2 and adding 5 to positive 2, we can see that x needs to be between 3 and 7. So that idea of radius convergence kind of makes sense. Our center point is 5, and a radius of 2 would be 2 units left and to the right of x equals 5, and that gets us 3 and 7. So we see that the series is absolutely convergent on the interval from 3 to 7, not including the endpoints. Now, from the ratio test, we also know that the series is divergent whenever that ratio is greater than 1. Knowing that the series is divergent whenever the absolute value of x minus 5 all over 2 is greater than 1, we can even solve that inequality to give intervals where the series is divergent. This is equivalent to the absolute value of x minus 5 being greater than 2, and that can be split up into two inequalities. Either x minus 5 is less than negative 2, or x minus 5 is greater than positive 2. We can't turn that into a sandwich inequality in this case. Solving each of those inequalities separately, we can just add 5 to both sides. So we know that the series is divergent on the interval from negative infinity to 3 and from 7 to infinity. And we'll use the union symbol to join those together. But what about when we have x equal to 3 or x equal to 7? In those cases, that gives us this ratio equal to 1. And that is the one case where the ratio test is inconclusive. If that ratio, the absolute value of x minus 5 all over 2, equals 1, solving the equation for x, we have the absolute value of x minus 5 equal to 2, and that gives us x minus 5 equal to negative 2 or x minus 5 equal to positive 2. Once again, those are the endpoints of our interval of convergence, 3 to 7. The only two numbers left on the number line that we don't know if the series is convergent at, 3 and 7. Well, why don't we try plugging those numbers into the series and see if we can use a different test rather than the ratio test to determine whether it is convergent. Well, when x is equal to 3, plugging that in, we have 3 minus 5 to the n, which is negative 2 to the n. So our series becomes n squared over 2 to the n times negative 2 to the n. We can simplify that series a little bit and rewrite that negative 2 to the power n as being negative 1 to the power n times 2 to the n. That cancels out these 2 to the n's. This gives us the alternating series negative 1 to the n times n squared. But this particular series is diverging because of the test for divergence. We can very clearly see that each of the individual terms, negative 1 to the n squared, is not approaching 0 as n goes to infinity. So this power series is going to be divergent when x is equal to 3. What about if x is equal to 7? Well, when x is equal to 7, this is even easier, because plugging in 7, we have 7 minus 5, that gives us 2 to the n. Well, the 2 to the n's cancel out immediately, and we're just left with the sum from n equals 0 to infinity of n squared. Once again, by the test for diversion, this is divergent. So there we go, we've tested the endpoints. Now we can go ahead and answer the question for what values of x this is convergent, since we know every possibility for the real number line. So we say that the power series n squared over 2 to the n, x minus 5 to the n, from n equals 0 to infinity, is convergent on the interval from 3 to 7, not including either endpoint, with a radius of convergence of r equal to 2. Why don't we take a look and see what that looks like in Maple so you can maybe see that interval and radius of convergence. All right, once again, I've got that series prepared here, n squared over 2 to the n times x minus 5 to the n. And here's what the first 5 terms look like. When n equals 0, though, the first term is just going to be 0, so it's kind of hidden. It only looks like there's 4 terms. Now, let's try plotting that. And I'm plotting this from x equals negative 5 to 10, so that interval from 3 to 7 is sort of somewhere in the middle of the graph. Let's see what this looks like. Okay, well, you can see the center point there is x equals 5. And let's animate this by going through all of the different partial sums all the way up to the sum from n equals 0 to 50. And sure enough, maybe if you just zoom in here a little bit, this might help a little bit. So here's that interval from 3 all the way up to 7. Unfortunately, this graph here just kind of leaves off the top of my axis way before I get to 7. But watch what's happening. It's not just converging over a radius of 1, like our first example. This is converging over a radius of 2. Watch this again. It's converging beyond 4 and still converging even as we get closer to 3. But it's getting a little bit tougher to see that convergence. It's converging slower and slower over the last little bit of that interval. Maybe if I were to try more than just the first sort of 50 partial sums. But there you go. You see that the interval is not just always going to equal 1. In this case, the radius is equal to 2. It's just got a little bit wider interval of convergence. Now, don't forget to test those endpoints. In this case, it wasn't convergent at 3 or 7, but it is possible to be convergent maybe at one endpoint and not another. Let's just take a look at one last quick example here. For what values does the power series x minus 2 to the n all over n from n equals 1 to infinity converge? And note that this power series has to start when n equals 1 and not when n equals 0, since we are dividing by n. Well, It's pretty much just the standard thing to go ahead and try that ratio test and see what comes from that. Now, it sort of becomes standard practice that whenever you see this fractional expression in your power series, it's probably best to just go with an plus 1 times the reciprocal 1 over an. And then we'll try to simplify whatever factors we can and use our absolute values wisely here. So right away, n over n plus 1, well, we can't really simplify that, but we know it's always positive, so the absolute value of that factor is itself. And then we've got our x minus 2 to the n plus 1 over x minus 2 to the n. We can factor n factors of that in the denominator and numerator, and that leaves us with x minus 2 to the 1. And we can't forget to keep that in our absolute value. Just like in our last example, we can move that outside of the limit and take the limit as n goes to infinity of n over n plus 1. Now, we could use L'Hopital's rule for that limit, or we could take n over n plus 1 and divide by the highest power of n in the denominator, but in either case, that limit would equal 1. So by the ratio test, we are left with x minus 2 in absolute value, and if that is less than 1, it is convergent. Well, right away, that gives us our radius of convergence. If we want to find our interval of convergence, then it's fairly quick to do that by just knowing that this is a power series centered at x equals 2. And using a radius of 1 on either side, that gives us our interval from 1 to 3. So we could reword that statement and say that it is absolutely convergent on the interval from 1 to 3. But we still need to test those endpoints for convergence. So let's take a look at when x equals 1. Well, when x is equal to 1, this gives us a series negative 1 to the n over n. We might recognize that. That's the alternating harmonic series, and we know that that's already convergent. What about when x is equal to 3? Well, when x is equal to 3, this is just the series 1 over n from n equals 1 to infinity. Hopefully you recognize that right away as just being the harmonic series, and we know that that is divergent. So that means that we have a radius of convergence r equal to 1, and it's absolutely convergent on the interval from 1 to 3, but it's also convergent at one of those endpoints. So to answer the question fully, we can say that our power series is convergent on the interval from 1 inclusive to 3 non-inclusive, and we can say that the radius of convergence r is equal to 1. Now, we've done a couple examples where we've seen convergence either over all the real number line or over a couple intervals, but let's not forget that there's also that other particular case of power series where they're only convergent right at their center and their radius is equal to 0. Now, they're not very exciting. I wouldn't want to maybe show you one of those on Maple because, well, the graph doesn't converge. The partial sums don't look anything like each other except that they all pass at the same point. It's not quite as exciting, but don't forget that those kinds of power series also do exist. Well, there we go. That's an idea of series, but with a variable. And rather than thinking about partial sums getting closer to a number, you can think about their graphs. Partial sums of a power series all look roughly the same on their interval of convergence. Now that radius can be pretty small. Maybe it's only going to look very, very similar over a tiny interval. But there are some pretty interesting power series that as you start to include more terms in your partial sum, that they actually have the same graph over all of the number line. And that's going to be really useful when we take a look at Taylor and Maclaurin series in a future video. So stay tuned. Thanks for watching, and I'll see you in the next video.